I'm interested that you mentioned psychiatric disorders. It's something that there seems to be a colossal gulf at the society level between physical and mental disorders, and I would have thought it might have been similar in the scientific community as well. I know at the clinical level too, there's a big gulf.
Well, I mean, there's a big gulf in terms of basic research in psychiatric disorders for the very obvious reason that basically you have to do your research in humans. You know, if I'm working on cancer, I can do, in principle, studies in the whole range of animal models, and I can take the basic science that my colleagues do in virtually every area of biology and apply it to cancer. But if I'm going to work on behavioural and thought process disorders, then I can learn the neurophysiology from a mouse to some extent, only to some extent, and perhaps more sophisticatedly from more sophisticated animals. But eventually, if I'm going to tackle the problems, I'm going to have to tackle them in humans, and that's much harder. I mean, it's harder even to the extent that it's hard just to define the nature of the pathology. You know, there is clearly, if you like, a biochemical, a molecular cell biology basis for major psychiatric disorders. I mean, that's fairly clearly defined. It's most obviously defined for schizophrenia and depression, where the biochemistry is moderately well understood and leads to rational drug use, sort of. But it's really hard. I mean, you know, if you're supposing you were wanting to do a research project on obsessive compulsive neurosis, which is actually quite a common problem, nobody has any idea of what the neurological basis of that is, what the biochemical basis of that is, because we don't really understand what the biochemical basis of behaviour is. So, you know, where do you start? Yeah, you're right, we do neglect those areas, and I mean, it doesn't help, of course, by the fact that the community has perhaps less understanding. You know, they understand cancer and die of cancer, they don't understand obsessive compulsive behaviour disorders very well. But even if they did, and supposing there was huge support, and the government said, look, we'll put $50 million extra a year into research in that area, it wouldn't lead to anything very much, because there isn't a very good approach to find. The technology and changes, and we can now do brain biochemistry on the run in humans. It's phenomenally expensive, it's invasive, and we don't quite know what the answers mean, but we're starting to do it. I mean, we can do, basically, we can real-time image the thought processes, if you like, with PET scanning and radioisotopes. And what started off as an investigational tool looking at how, for example, the visual cortex works and how you can see, has now become an investigational tool where people are looking at what goes wrong in epilepsy, schizophrenia, and other biochemical disorders of brain thought processing. And you can also use some fairly sophisticated neurophysiological tools. I mean, my wife, for example, is a teacher who looks after kids with learning difficulties, and one of the problems that has become clear in that area is that the buffering process that you use to process information as it comes in from your special senses, particularly hearing, can be biochemically disordered in these kids that have speech-language impairment. And you can actually measure that. You know, it's to actually turn it into an analogy. If you speak a foreign language, when you're learning the language at the beginning stages, you can understand individual words. You know, you'll hear somebody speaking, and you'll hear a word in that language, and you'll say what the word is. But by the time you've caught up with that, they've gone 5 miles further on. And that's because your buffering capacity for dealing with foreign language is not very good. For the people who have speech-language difficulties, that buffering capacity is impaired for their own language. And you can actually measure this problem. And it has a neurophysiological correlate, so you can begin to understand what's going wrong. And the first requirement for fixing problems is to understand them, so that the moment we're at the stage in that sort of neurophysiological disorder that we were with cancer 150 years ago, where we're just beginning to understand that cancer was actually autonomous growth of cells from a particular tissue type. Before that, cancer was totally not understood. So, you know, in 150 years' time, I'm sure that we will have the same ability to at least categorize and possibly also manage some of these disorders, whether it's neurophysiological, but, you know, we're just that much further behind in the process. I mean, if you'd asked me the same questions about immunology 100 years ago, you know, we would have been wandering around in the dark, and we'd say we don't have the tools to understand this, we don't know what's going on, because we wouldn't call it immunology. You know, we say we've got a patient who's can't fight off infections. We would at least know, we would know what infections were, because we'd have found that out about 50 years previously, but we wouldn't have a clue how the body defended itself against infections. So we would have, anything we did would have been guesswork. But we've learned a lot about how the immune system fights off infection now, so we can sort the problems, and when people get problems in that area, we can categorise them, we can say this is what the problem is, we can try treatments. It depends whether you take a long-term view of the problem or short-term, whether you've actually got a problem or not. Yet neurology is a different stage of evolution as a science.